First of all, big thank you to all the people that contributed to Piazza. We had a very intense week there. I think it helps a lot on our side to understand where the problems are, and on your side for like helping each other and getting a better grasp of the whole topic that we're discussing here. So let me directly dive in. There's just one small comment related to Piazza. Some people started to ask a question which was like with the title Doubts about Lecture XY, and then there's a series of a couple of questions. I think it would be much more helpful for us and for everybody if you make individual questions and give them kind of a descriptive title that we can assign them to the right people and also group them much better. It's easier for your colleagues to follow as well. Then some of the most important questions that were discussed. Let me quickly go through them here again. First one was related to questions with SCARA robot arm. And the question there was primarily related to geometric and analytical Jacobian and why these two are the same. If you look at the SCARA arm here, we have like 3 degrees of freedom for rotation, which are, let me pointer here. So we have 1 rotation, 2 rotation, and 3 rotations, so 3 degrees of freedom for rotation and 1 linear direction, which means that the SCARA arm with this type of actuation can move this point here in 3 directions. So we can control 3 positions. At the same time, we can control 1 rotation around this vertical axis, because all these axes, they are parallel. In other words, what we have here is a problem which has 3 dimensions in position, but it has only 1 dimension in rotation. So it's kind of a 2.5T problem with a rotation in addition to that. So it's 4 degrees of freedom in that sense. So that means the rotation is only a 1D problem, so we don't have to deal with SO3. And as we know, if you have a planar problem, then geometric and analytical Jacobian are the same, and hence the same happens here also for the SCARA arm. Then the second question that I think is important to rediscuss here is related to dimensions of Jacobian. When we look at the Jacobian, we typically had 2 different kinds of, we had geometric Jacobian and the analytic Jacobian. And what was different there was primarily that on one, we had the dimension of position orientation of this end effector. So with this XE, we typically denoted a position, RE, plus a rotation like phi E. As we know, this rotation, it's not similar to a position where we have Cartesian coordinates that directly parameterized the end effector position, in which we can do time derivative and we get velocities. There's nothing such as an angle. Nonetheless, what this is kind of a 3-dimensional rotation. It stands for that. But if you look at velocities, so x e dot, clearly we have r e dot, and we have omega e, so the end effector angular velocity. On the other hand, we had here the parameterization, so chi e, and this chi e had a parameterization for the position of the end effector and the parameterization for the rotation of the end effector. And this rotation parameterization could be very different. It could have been like quaternions, Euler angles, whatever, and that changes the dimension. The second part that we see here is, here we have the number of Qs. And this number of Qs means really all the Qs that we use to describe the complete kinematic structure of the robot, and not only the ones that a certain position is depending on. I want to illustrate this with the following robotic system. So this is a robot which stands on a table, and we have two arms. So we have one arm here, and we have one arm here. So what we need to have is we have a Q left hand and a Q left arm and Q right arm, which are used to describe the kinematics of these individual arms. So if I have my complete set of generalized coordinates, these are the Q's of my right hand or right arm and my Q's of my left. If I want to derive now the Jacobian of that one end effector, which obviously only depends on this right hand Q's, nonetheless, we're taking all the Q's as we have them here, so the dimensionality of this Q will always stay the same. The dimensionality of this Jacobian will always stay the same because we have the same number of Q's independent of which Jacobi or which position that we're looking at. So this is what we have here in blue. That depends on the kind of robot that we have, on the number of joints that we have. What we have here on the left depends on the task and on the description of the task. And then the last element that I think requires a little of discussion was a question: what is the n, the basis that we have to express this n, whether it's k minus 1 or k, for defining this rotation axis? And there was a small discussion ongoing in Piazza. I think like the most intuitive explanation is the following. If I look at all the drawings that we made with like multiple links, we typically had the main axis of the link corresponding to one of the axes of our coordinate frame. So we have a coordinate frame here for k minus 1. So here are the e of the k minus 1s, and here are the e of the k's. However, the rotation axis in these two frames, so the rotation axis here and here, they're aligned. So whether you express n in k minus 1 or n in k, it's typically the same because they're rotated with respect to each other around that one axis. So the rotation matrix that transforms from k minus 1 to k or from k to k minus 1 has this 1, 0, 0 entry on exactly that direction that defines the rotation axis. So that's why it really doesn't matter where you express it. Just make sure that you have it consistent, and if you have here k minus 1, that you have also here k minus 1. If you put here k, that you also have here k. But other than that, you can't do anything wrong. So these are the most important elements that were raised in Piazza. Some more will be discussed tomorrow during the exercise session. We are now diving into the quiz that we looked at, which was essentially one big quiz, but split into 3 different subparts. And this is something that will for sure in a similar way come also in the exam. So what we're interested in is how is end effector motion related to joint space motion? How can we do this inverse differential kinematics? And how can we utilize a redundant configuration of an arm to fulfill multiple tasks? And what is the difference between these different objectives that we can possibly satisfy in such a setup? What we're looking at here is a robot arm which has like 3 degrees of freedom. So joint 1, 2, and 3. We don't look at the end effector at all. We have the coordinates, so this QT, which is in essence like 30 degrees, 60 degrees, and 60 degrees, if you want to draw it up the right way. And we give you a target end effector velocity defined as 1, 1. So we're only interested in the position, so in the velocity, not in the angular rate of the end effector. And what we want to figure out is what is my Q dot. So we know we have the relationship that this R dot is equal to J times Q dot. So if I would like to figure out what is my Q dot, I have to take the inverse of the Jacobian. If the Jacobian is not quadratic, not directly invertible, what we have to do is to take here a pseudo inversion of that and multiply this with R dot. So what we need to do is take the arm and figure out what is my Jacobian and what is the pseudo inversion of that Jacobian. And this is what we do here. So we start to figure out the end effector position as a function of this phi1, phi2, and phi3. We did this already several times, so I think I don't have to dive too much in detail. So we have always the sine component, L times sine component in x direction, and we have the 1 plus cosine component in y direction. There was a question which is whether or not we should always take the pseudo inversion even if the Jacobian is invertible. So if the Jacobian is invertible, then the pseudo inversion will give you the same result. So if it's invertible, you have only one solution, and then you can take this one solution. So the least square optimal solution of that is the same solution. So that will not change anything. And the second question was whether or not you should be able to determine a pseudo inversion of a Jacobian in the exam by hand. So one thing that we could ask is that you do this with your calculator. Typically, we're not interested whether or not you can do the right evaluation of a numeric algorithm. But what we're interested in is that you are able to write it up the right way. So if you write up how you determine the pseudo inversion of a Jacobian and you just like add this in the formula, then that's perfectly fine. And then the question is, in which way should RE, so should the Jacobian be defined? I guess this was related to Jacobian geometrically or analytical. And this is again, like for a planar problem, it's one and the same. And we will discuss most likely planar. We have to discuss planar or pseudo-planar problems, otherwise you can't do it by hand. The question is whether a calculator is expected to be able to calculate the pseudo inversion. Well, you can directly use the formula of the pseudo inversion if you want, and then it's only matrix multiplication. And I think a matrix multiplication should be doable by a calculator. So let's move on. These specific exam-related questions also something that you can put on Piazza, and then we can discuss it for everyone in a written way. All right, so what we do now is we take our R, we take the partial derivative of dr dq, because it's a planar problem, we are allowed to do this. So what you end up with is we have, so this first part is like the first line partial differentiated with respect to q1, which is phi1. So we have sine phi1 with respect to phi1 is cosine phi1, sine phi1 and phi2 is cosine 1 and 2, and so on and so forth. And we do this for all the elements. I think this should be something that is straightforward to be done for you. Now we have the Jacobian depending on sine and cosine functions. All we need to do then is to evaluate this. So we have now this Q, which we have to evaluate my Jacobian for that configuration. So this Jacobian here is still a function of the configuration. Now what we have to do is we have to evaluate it at the current configuration we are in order to get the Jacobian for this setup. So we take this Q at time t and we evaluate the Jacobian at time t. So we have to insert the angles here. And again, like these are 30 or 60 degrees angles, which means we have to know square root of 3/2 or 1/2 for the sine and for the cosine, and we enter these values in our Jacobian, and we get like the 3/3 Jacobian. Now, as you have seen, I've done this here as a 3/3 problem. So I looked at the whole position, although it's a planar problem. And one more time, in case you have your exam and you just look at these two rows, that's perfectly fine for me, as long as things are consistent. So you have to make sure that whatever you write up, you have a consistent formulation with your dimensionality of the individual Jacobians, positions, and joint space definitions. All right, now we have the Jacobian, and all we need to do is take this and evaluate this formula up there. So we go and we have to take the pseudo inversion of that. This is straightforward. So the pseudo inversion J plus is equal to transposed J transposed -1. So what we're doing here is we're creating with this J transposed, we're creating a square matrix which is invertible. Then you invert it, then you do a Jacobi transpose pre-multiplication. Now what you do is we take this pseudo inversion of this Jacobian and multiply it with 1, 0, and what we'll end up with is this 3/1 vector. So we have now a solution for Q dot that satisfies that task. So we want to achieve end effector velocity of 1, 1, and what we figured out is a Q dot which satisfies that one task. And I can check this. So what I can do is I can take the Jacobian at this time t, Q, multiply it with this Q dot that we calculated here, and what you end up with is with this one, velocity. So let me quickly answer the questions that are in here. So the first question is, why don't you have the rotation component in omega, and whether or not my WE should be R dot E and omega. This would be another question that I could ask, namely, you want to have the end effector velocity R dot plus the end effector angular velocity W. However, what I asked here is only the velocity, the linear velocity of my end effector. I leave it free what kind of angular velocity we have at the end effector. So that can be varied depending on the question. So always read the question precisely. And that means if you have now positions only, so we have 2 degrees of freedom that we want to achieve at the end effector, but we have 3 joints that can satisfy this, that means we have this redundancy that makes the problem a lot more interesting. So there were some more questions related to the pseudo inversion. Let me do the following. I will post a link on Piazza related to the different pseudo inversions that exist, that you have that for systems which are column rank deficient and systems that are row rank deficient. The difference there is, in essence, if you have something which is which has less degrees of freedom than what you want to achieve, what you have to do is you have to find the solution which gets closest. So you have to find the Q dots which get closest to the solution. And the other way around is if you have multiple more degrees of freedom that you can modify and less tasks that you want to satisfy, then of course you can have different solutions for the problem which makes the error to become 0. So what you have to take, or what the pseudo-inversion is taking, is the least square minimum solution of that. And one is this, what I wrote here, and the other one is essentially the reverse of that, where you have J transpose J inverted times J. So let me have here a very short break, 2 minutes, because we're gonna have a presentation by a colleague of you who was supposed. Darius, can you share your slides?
Yes. Can you hear me?
Yes, we can hear you.
Perfect.
Give me 1 second. I think I have to make you. Okay, now you should be able to share your screen. So, yeah.
Does this work?
Yes.
Perfect. So thank you for this opportunity. My name is Darius, and I'm part of the team Groundhogs that formed at ETH to compete at the Not the Boring competition. So this competition, this competition is held by the Boring Company, one of the companies of Elon Musk, and it's about building a tunneling machine that can build a self-supporting tunnel structure. So there will be a competition in the Mojave Desert in the US where we need to dig a tunnel with the length of 30 meters and the diameter of 0.5 meters. So this is pretty small. This is considered micro-tunneling. But it's about having a concept and the design for a tunneling machine that can be as fast as possible. So this is also what it's about. It's going to be about who is the fastest to complete the tunnel and who is the fastest to have a driving surface in the tunnel where the Boring Company can drive a remote controlled car through the tunnel. So what's also going to be important is that we can dig a tunnel that is as accurate as possible, so we know where to start and where to end, and we need to be as precise as possible. This is also going to be one of the main challenges that we can think of right now. We would also like to be able to tunnel while having a structure built that can support the tunnel. So, so we can be as fast as possible. We want to really be digging and constructing at the same time. For that, we would also possibly need or use the excavated materials. So we think this is going to be really interesting from an engineering point of view. That's why we are looking for new team members that can help us keep up with this timeline. So we should have a design due this month and then the final design in January, so we can go to the Mojave Desert in summer and compete at the competition. Right now, we are a team founded of 6 members of the Swissloop team that you may have heard of. And we have now 15 other team members that joined us to help us have a great adventure this year by building this tunneling machine and going to the US and competing. So I would really like to invite you to also join us if you're interested in a competition if you're interested in working within a multidisciplinary team, and if you want to have some real life experience by building something outside of class or lab within ETH. So if you're interested, please don't hesitate to contact me, and we can then have a discussion about what we could provide you with and what you could help us with. So that's it from my side. Okay. Thank you very much.
Thanks a lot, Darius. So we have heard now the third student project. So for those who are interested in like doing something excited, feel free to join one of them. I think it's a great opportunity for all the students. Now let's go back to the exercise that we looked at before. So what we have now is we've calculated a solution which satisfies this task that says like we want to move with a velocity 1, 1 at the end effector, and what the result is a q dot which satisfies that. And it's actually the q dot which is the least minimal q dot that satisfies that. This is what this student version is doing with the solution. As I said, we have 3 degrees of freedom in our arm, but we only control 2 degrees of freedom at the end effector. That means we have essentially one direction which remains free. In other words, we can optimize additional objectives in the whole inverse kinematics or inverse differential kinematics problem. And that's what we asked as a second question. Like the second question was, well, we want to achieve the same end effector velocity, but now we want to also have a second task which says that the first and the second joint should have 0 velocity. Now, what does that mean? If I say the first joint should have 0 velocity, what I want to have is a task description for that. So I want to figure out what is the Jacobian for that task and what is the goal on that task. And if I just have to select a joint, this Jacobian essentially boils down to a selection matrix. So this Jacobian that we have to write down here for this one task is essentially 1, 0, 0, 1, 0, 0. So what it's doing is this first row selects joint 1, and the second row selects joint 2. And the objective is, the goal is that both of that Q1 dot and Q2 dot are 0. So that's how we converted this text into a task level description with Jacobians and W's that we want to achieve. And now in this question, we say we don't give priority. We say the second task has the same priority. So we want to achieve the first task and we want to achieve the second task, both with equal priority. So what we need to do is we need to stack this Jacobian. So we have to stack them, J1 over J2, and we take the Pseudian version of that, and we multiply this with W1 and W2. So we have here, this is 1, 1, 0, 0. And what we will have at the end is, again, a solution, 3 velocities for Q dot 1, Q dot 2, and Q dot 3. Now the question is, how does that solution that we got now satisfy the task objective? So let's again check the solution. We take now these Q dots and multiply our J1 and J2, the stacked vector, with this Q dot. And what we'll end up with is with the following. So we have here 1.039, 0.933, whatever. So we have here on these two things something which is close to 1, 1, but it's not exactly 1, 1. And here on the bottom, we have something which is close to 0, 0, but it's not quite 0, 0. So what the optimization is doing is it figures out the Q dot, which minimizes these errors, which brings the solution as close as possible to W1 and W2. So let me go to a few questions that were asked here. First one, how do we get J2? I hope I explained this now in detail. If J2, if we have a text description of a task you want to satisfy. For example, I want to have a velocity at a certain point. I have to figure out a Jacobian that relates to that one task. If I want to have a joint to have a certain velocity, I have to figure out the Jacobian that relates to that task. And this is then a selection matrix for that one joint. Then the second question was, shouldn't W2 mean the end effector velocities? Well, W2, so what we did here was a general setup. I say every task, a task is composed of a Jacobian and a W. And the W is the goal that we want to achieve with that task. It can be that this has end effector velocities, R dots. It can be that this has end effector angular rates. It can be that we have here joint level velocities. Like anything that can be somehow made up Q dots through a linear multiplication. I mean, the J is nothing else than a mapping from one space to another space. So anything that relates through a Jacobian to a task description from joint level description. And then W1 and W2 refer to position. So then that's a good question. The question was, one relates to linear velocities, the other one relates to joint level velocities. So they have, first of all, they can have completely different ranges. They can have completely different units. So I can either give the velocity, in radians per second or angles per hour or whatever. This is not defined here. And that means the least square optimization, of course, figures out a different solution depending on the units that I'm taking there. So in many applications, what one is doing is, for this pseudo inversion here, we are using a weighting matrix. And this weighting matrix essentially normalizes this minimization problem, that we are not comparing angles against linear velocities and the other way around. So we maybe scale it to max values or something like this. But that's one of the issues that you have it, that if you are like combining multiple tasks with different dimensions. And then the last question was whether W can be something weird like the sum of different joint velocities. This is absolutely possible. So for example, if I would ask you, make sure that Q1 dot plus Q2 dot together are 0, I can figure out a Jacobi for that. And this Jacobi for that is, I take my first Q1 dot, I take my Q2 dot, and I don't take a Q3 dot. I can also want you to figure out a solution where Q1 dot is equal to Q2 dot. And what you could do for this is we say, okay, my Jacobian now is like 1, -1, 0. Something like this. So what you cannot do is you cannot have complex functions, right? You cannot have squares or whatever in there because you have to somehow figure out the selection matrix or the Jacobian to relate this to the description. So the second solution was we just equalize all priorities and we figure out which Q dots figure out or are satisfying this task as well as possibly in a least square sense. That naturally raises the question for a third solution, namely that we give different priorities. We say, well, the second task of first and second velocity to be 0, it is important, but it's not quite as important as the first task. So I want to make sure that like my end effector really tracks my end effector position or my end effector velocity. And I want to make sure that like the second task is just like fulfilled as well as possible. So what I can do for this is the following. We essentially start, again, we have the Jacobi 1, which gives, if I want to have my Q dot, I have to do my Jacobi 1 pseudo-inversion times my W1. But as we've seen, this is not the only solution. There is a null space 1, which allows us to modify the solution with a Q0 without actually violating the task. Now we can have the second task, and for the second task, what we have to do is like, we want the second task, so this J2 times Q dot, which is, if I take this upper solution and put it in here, so it's J2 times J1 plus W1 plus J2 times N1 times Q0, and this we would like to be W2. Now what I want to figure out is what is my Q0. So I solve this for Q0, which gives my W2 minus this first part, J2, J1 plus W1, and I do the pre-multiplication with J2, N1 pseudo-inversion. And then what I need to do is I take this and I insert it in here and I get my Q dot. So let's do this. So I insert this in here and I will end up with this formula here. I wrote this for you. And in here again, we have a couple of pseudo-inversions, a couple of null spaces. And if you do this, you will end up with a solution Q dot, which is this prioritized solution, which is slightly different to what we have seen before. Before moving on with discussing these solutions, again, like a couple of questions that were raised here in the chat. Question 1 was whether we can include dynamic constraints as tasks. So for example, torques, torque limits, stuff like that. You have to wait for this. In 2 weeks, we're going to discuss this. So the exact same procedure that we apply here for kinematics, it can be applied also for dynamics, but there we have to include the full dynamics equation as constraints, but then you can formulate more or less the same prioritized optimizations that we have here. And how do we get N1? We have displayed a null space before in like one of the exercises that we looked at previously. The N1 here can be either calculated directly by I minus N J plus J. What this will give you is a matrix which has the same dimensionality as your number of columns in your J. But if you look at this null space matrix here, this null space projection matrix, we see we have 3 columns. But if you look at these 3 columns, we see that they are essentially linearly dependent, right? If I multiply the first column by -2, I will end up with a second column. If I multiply the first column by 2, I will end up with a third column. So in other words, the rank of this null space projection matrix, so the rank here, is only 1. So what does that intuitively mean? We have now a projection matrix which projects the solution into a one-dimensional direction. So that means we have a direction which is a linear combination of my Q dots on which I can modify the solution. I can modify my Q dots without actually modifying my W or my J times Q dot. And this is nothing else than what we have given through the dimensionality of the problem. So we have 3 degrees of freedom in my joint space. I occupy 2 of them because I want to have my end effector following something. which leaves us with one direction, that we can still change the solution completely without changing this end effector task. And this is exactly the direction that we see here in this N. There's also other ways how you could like intuitively figure out this N. I'm going to show this later if you have enough time, or then next time in the session. So there's one question here which mixes up inverse differential kinematics and inverse kinematics. So maybe I can, time-wise, we don't have too much time left, so I will pick this up also in Piazza. Maybe you can post, Ulrich, if you can post this on Piazza, we can discuss this for everyone. Let me spend the last 3 minutes on discussing the solution. So first of all, we check it here. So if I do now multiply my J1 and J2 with this Q dot prioritized, as I can see, the first task here, this is completely fulfilled. So I make sure that my first task will stay there. The second velocities, well, they're close to zero, but they're not quite exactly zero. So if I compare now these 3 different solutions here, I think what is interesting is to look at the errors of these individual tasks. So let's have a look at the first, this Q signal. If I look at my Q signal, what I have here, so my Q signal, this essentially tried to satisfy task 1. It didn't care about task 2 at all. All it cared about was minimize the Q dot which satisfies this first task. So if I look at the next one, at the stacked solution, where we wanted to achieve the minimal error in the first task and the minimal error in the second task. And the third one wanted to make sure that the first task is completely fulfilled, but then I minimize the error of my second task. So if I compare this now, if I look at these 3 Q dots, or this should be Q dot here, of course. If I look at these 3 vectors here on the left-hand side, I will immediately see that the first vector is the shortest. So this is the minimal Q dot that actually fulfills my first task. If I look at the errors here on the left-hand side, I see that the first one satisfies task 1, so we have 0 error here. The last one also satisfies task 1, we have 0 error here. That one sacrifices a little bit on this task 1, so we have an error here, but in return we gain a lot that we can also decrease the error of my second task, while this third one, which ensures that my first task is satisfied, can also reduce the error on the second task compared to this first one, but never quite as this one. So the sum of these 2 errors here is larger than the sum of these 2 errors. So that's how you can start now balancing different tasks against each other, different priorities. Some you have to make sure that this is for sure fulfilled, others you don't care too much. And that will also be then a very important topic when you're discussing dynamics. So one of your colleagues asked, can you also do this for dynamics? So imagine you have a robot that can also only achieve certain torques or can only have certain joint level limits. And you want to make sure that this is for sure not exceeded. Then this formalism with priorities really allows you to do this in a very clean manner. And we can have arbitrary tasks, in particular for very complex multi-body, multi-link systems, like a humanoid or legged robots or whatever. You have typical multiple objectives that want to be fulfilled at the same time. And this is like a formalism that allows you to do this. With this, we're again done in the right time. I will, since we didn't have time to go through the possible exam questions, I will upload this again on Piazza. So possible exam questions will be exactly what we went through now, but for example, for another kinematic structure. So we had an excavator in 1 year. We looked at this excavator from the side. We asked questions like, what are the end effector Jacobian for position and rotations? And then you had to figure out like inverse differential kinematics for certain tasks. You had to look at whether or not this is redundant and then have a stacked solution or a prioritized solution. So really something that I would say right now, if you have understood like this session that we did today, you can very easily go also through these exam questions. And with this, I'm closing here. And thank you all for attending, and see you next week when we're gonna have our first session on dynamics. Thanks a lot, everyone.